Hi guys, I welcome you all to another session on Econometrics. Now, this session that we're going to have is going to be our last session in this course because this is an introductory course. However, there's one small issue that I've not covered, which is model misspecification. Now, it's a very small part of the course. It's just a couple of pages, and it's also given in my class notes, so you can follow it through there. Apart from that, what we have covered in the entire course is first beginning with the hypothesis testing and starting with two variable regression, then progressing to multiple variable regression, the hypothesis testing in that multivariable testing, then introduction of dummy variables, then moving on to different functional forms, and then dropping the assumptions, dropping the assumption that we had taken during the classical linear regression modeling. Now, the first assumption that we had dropped was that of multicollinearity, and then we observed that how to detect multicollinearity, what are the consequences of multicollinearity, and then going forward towards how do you find. So, in this particular chapter, we are going to cover autocorrelation. Now, if you remember, one of the classical linear assumptions was that of the fact that the error terms are not correlated. So expectation of j is equal to zero. So this was one of our cardinal assumptions during the classical linear regression model, which we are going to violate in this chapter. And again, the procedure in this particular chapter is going to be similar to what we have already done in the previous chapters, which is that we will understand the nature of autocorrelation. Then we will see that how do you detect autocorrelation, what are the diagnostic tests, and then moving forward to what are the remedial measures, and in between we will see what are the consequences of autocorrelation on the blue estimates. So this is going to be our framework of the chapter. Let's begin with the very basic of what we had assumed. So as I told you, that we will be starting with the nature of autocorrelation, and moving on to the consequences, and then detection, and the final part will be the remedy of the problem. So perhaps this order is similar, as I told you in the last two chapters as well. This order is going to be the same for all the violations. The approach to this particular chapter is quite similar to that of heteroscedasticity, that you really do not know whether your data suffers from heteroscedasticity or autocorrelation. So what you can do is actually run the normal regression with the assumption that your data does not suffer from this problem, and then move on to further diagnostic tests, and then perhaps if the diagnostic test kind of confirms or kind of hints towards the existence of the problem, then what you can do is probably transform the data. In the chapter of heteroscedasticity, if you remember, we had two kinds of ways. One was either if you knew that what is the variance, the error variance, or the variance in the data. On the second case, you did not know the variance in the data, so you estimated that or you assumed that, and appropriately you divided the entire data with the variance or the standard error, so that you could come out with a homoscedastic model. Similarly, in this chapter as well, the kind of intuition is very similar to that you would need to estimate the relationship between the error terms, and on the basis of that estimation, you could have a different kind of a model, which we will call as a GLS model. Remember, in heteroscedasticity, we had something called the weighted least square. Here we will have something called general least square, or the general difference least squares. Let's start our analysis. So the nature of autocorrelation. In this entire chapter, what I will do is I'll perhaps will be comparing this chapter with heteroscedasticity a lot, because the kind of treatment is quite similar to it. So if you remember, in the previous class, I had told you that heteroscedasticity is a problem which is more persistent and probably as a rule in cross-sectional data. In case of autocorrelation, you will find in case of time series data, you will definitely have this problem of autocorrelation. We'll see why you have a problem of autocorrelation in time series data, but that's not the only case. You also have spatial correlation. So in cross-sectional data also there might be a case of autocorrelation. Now, what is autocorrelation? Autocorrelation, the assumption of no autocorrelation means that there is no the product between the error terms has no relationship. Or if you simply term it, what we mean is that a disturbance term has no relation with the disturbance term of any other observation. So you have a disturbance term for xi, so x1, and you have x2. So this error term or the disturbance term, say, is u1, and here it's u2. These two error terms are completely uncorrelated. So the disturbance term relation of any observation is unrelated to the other observation. Let's try to put it in a different example, giving an example. Now, suppose there is you are estimating a production function. In this production function, you have regressing the output y1, L, and k. So this is your production function. This is what you are regressing. Now, suppose you have you're saying that there is no autocorrelation. However, there is a strike in a particular period, or suppose take the period of this lockdown. So suppose you have this lockdown period where you have zero labor, you have zero capital, and your output actually decreases by a huge margin. Now, what this autocorrelation assumption is assuming that if in this t period there is no output, or there is some depression in the output, then that has no relationship at all with the output that is going to be there in t+1. However, that is not going to be the case. You can pretty much imagine that because of the fact that the base is so small, and the fact that as soon as now the lockdown is over, what will happen is that there will be an influx, which is not actually happening, but there will be a huge pending demand. However, the supply was not there, so the manufacturers will run towards supplying that, completing their supply chains and trying to produce and make up for whatever has happened, whatever the shortfall happened in this particular period. So actually, what has happened in this particular period, in time period t, is definitely going to have an impact in t+1, and that is basically called the inertia effect. The inertia effect, that if you find economic graphs, you will find that economic graphs are actually either in increasing order or in decreasing order, but there is a kind of a trend, there is a kind of a seasonality to it. So that is where there is that the fact that the errors are actually related to each other. You cannot say that they are completely unrelated. Even in cross-sectional data, you will find that there is some kind of association. Why? Let's take an example that suppose my neighbor buys a Mercedes. Now, if he buys a Mercedes, then of course, as a ratchet effect, in economics we call this as a ratchet effect, I will also be, because of the social pressure created, I might be also pressurized to increase my standard of living. That supposedly actually happens with a lot of high-end societies, high-end society residential apartments, something like that. So the consumption, and that's a cross-sectional data example, that the consumption of one family actually should not have effect on the consumption of any other family, but actually in real life it does. So that kind of an effectivity is actually called as an existence of autocorrelation. This is an example of a spatial autocorrelation where you have cross-sectional autocorrelation, and when you have time series data, that's a time series autocorrelation. So in reality, this assumption does not hold true. As I told you, that if there is a strike in this particular period, then in the next particular quarter, you have to catch up for that backlog. Now, how do you analyze this? Remember, I'll bring you back to our discussion of heteroscedasticity. In heteroscedasticity, what we used to do is we used to plot the error square against each of the independent variables, or what you used to do, plot it against yi hat. If there is a relationship between these two, that ultimately give you a hint towards presence of heteroscedasticity, if it's increasing, decreasing, or if it's in some kind of a function. Here what we do is you can plot your error term against time. As I told you that this is more in case of a time series data. So if you find any kind of a relationship that exists between these, so in all of these A to D, you find that there exists some kind of a relationship between time and your error term, which essentially shows that yes, your errors are somehow related to each other. And if it's the case of no relationship, this is the case of no autocorrelation. So the analysis is very similar, and detection will also be very similar. So one of the ways to detect in case of heteroscedasticity was graphical method, which was formalized by Park test, if you remember. Similarly, we will have a graphical method in case of autocorrelation as well. Why do we have the problem of autocorrelation? One, because of inertia. As I told you that most economic time series have inertia or sluggishness. Now, inertia is the fact when you have an increasing graph. So you have something like gross domestic product, employment, money supply, all of them. When you have a upward turn in the business cycle, all of them will be increasing. So there is a momentum built into the system, and that momentum actually provides inertia towards the next particular value. So that leads to the presence of autocorrelation. Or autocorrelation can also be due to model misspecification. So if you have a incorrect model specified, where you have not included a particular variable which should have been included, or you have used a wrong functional form, in those cases what can happen is that the residuals can perhaps of the incorrect model can have a systemic pattern. So essentially what autocorrelation is a definite pattern of error terms. Now this error term, the pattern in the error terms can also be because of the fact that the model that you have picked is an incorrect model. So that can also lead to autocorrelation. Or you can have a cobweb phenomena. If you remember your microeconomics, you had a cobweb phenomena whereby this happens usually in the agrarian sector, whereby farmers actually take the previous year's price, and the previous year's price actually influences the sowing or the output in this period. Now let me give you a detailed example of this lag effect. This is called as the lag effect in production. Now suppose this year this is the current Kharif period going on. Suppose in the previous period, the previous agricultural period was the Rabi season. So suppose the farmers in the month of February, March, or March or April, they came up with their output of wheat to the market, wheat being a Rabi crop, and they found out that the market price for wheat is pretty low. So that gives them a hint that the prevailing market price or the previous period market price of wheat was low. So what they will do in the month of October, when the sowing season for wheat will come, the sowing season for Rabi will come, they will have that expectation built in that we realize a lesser price in the previous period, and because we realize a lesser price in the previous period, what will happen is that they will sow less of wheat. And if they sow less of wheat, what will happen next year in March or April? The amount of wheat, supplied wheat in the market will be low and the prices will be high. And because the prices will be high, next year when the sowing season comes, then the farmers will be tending to produce more, and then the same circle will keep on happening, and that is called as a cobweb phenomenon, because the supply in period T is actually dependent on the price realized in the previous period. So this, due to this lag effect that is there, and that also happens in a lot of economic phenomena as well. So because of that, you have the problem of autocorrelation. And lastly, you have the issue of data manipulation, where what you do is you do smoothing of data. Now, this is something that you will when you go to your master's level, especially at D school, there is a course as forecasting. So you will understand what smoothing of data is, what moving averages are. So when you actually smoothing data, what do you mean by smoothing data? Suppose you have monthly data with you, and instead of monthly data, what you do is take the average of 3 months and divide it by 3. So month 1, month 2, month 3, you divide it by 3, you get the average for this particular quarter. And if you see, the variation in these months will be much more pronounced as compared to quarter, because the quarter is a smoothened version of the average of and the average of these 3 months. So what happens is that although the data is smoothened, in this particular data you will find the problem of autocorrelation, because there is a systemic pattern in the error terms when you have smoothened the data. Now, if you see the examples of positive and negative autocorrelation, this is an example of positive autocorrelation, this is an example of negative autocorrelation. What you do is, another way of analyzing autocorrelation is basically analyzing either with respect to time, or what you can do is you can plot it with respect to the previous period error terms. And if the relationship is in such a way, then you have a positive autocorrelation. Remember, this is usually the case in economics. In economics, we usually have positive autocorrelation. There are lesser instances of negative autocorrelation, but usually we always have a positive autocorrelation. Coming to the second part, which is what are the consequences of autocorrelation. As in case of heteroscedasticity and multicollinearity, the problem does not affect linearity or the unbiasedness. Why? Because unbiasedness is a repeated sampling property. However, as in case of heteroscedasticity, what happens here is that the minimum variance property actually loses out. So your estimates are no longer blue. And if your estimates are no longer blue, that means your hypothesis testing is not reliable. And if your hypothesis testing is not reliable, your parameters are not reliable. Therefore, the problem of heteroscedasticity and autocorrelation must be tackled, because their existence or non-existence actually has a huge impact on the parameters. What happens is that in case of presence of autocorrelation, your OLS estimates are biased. And if you see my class notes, you will find out what is the kind of biasness that's there. It's there. If you scroll down this particular PDF, you will find out my class notes. And I've also estimated that how there is a built-in error, how there is a built-in biasness. Then, what happens is that your true variance is your estimators, they underestimate the true variance, and that means your true variance is much more than the estimated variance. Your estimated variance is lesser than your true variance. You are underestimating the true variance. Now, if you remember, this is exactly opposite to what happened in multicollinearity. In multicollinearity, what was usually happening, that your variance was exploding. In case of multicollinearity, your variance, your standard error was exploding, and because this was increasing, thereby you had something called variance inflation factor, because of which what was happening is that although your R square was, in case of multicollinearity, your R square was high, but you had few significant T. Here what you will get is that a lot of your parameters, because you're underestimating your variance, what will happen is your T values will come out to be significant. A lot of your T values will come out to be significant. When you see your regression analysis, you can actually see the difference, that in case of multicollinearity you will have very high R square, whereas few parameters will be significant, whereas in case of autocorrelation you will find out that your T values are inflated, and because your T values are inflated, most of your parameters will be significantly different from zero. However, that might not be the case. So you will be saying that you reject your null, however you might be making that error. So if your hypothesis testing is unreliable, your T test, your F tests are unreliable, and your variance, you're underestimating your variance, So because of this, your overall R square is also unreliable. So there are a host of problems which are caused by autocorrelation, as in case of heteroscedasticity. That means you need to solve that problem. Now comes the third part, which is how do you detect the autocorrelation. As in case of heteroscedasticity, there are certain diagnostic tools. You really do not know whether your data suffers from autocorrelation or heteroscedasticity. So what you can do is you can estimate it through the analysis of your sample errors. And this is how you do it. Suppose you have a regression whereby you have regressed your real wages on productivity. This is your normal regression. If you see the t-value is very high. It's extremely high, 42. Remember, I told you if the t-value is more than 2, then you will be rejecting your null hypothesis. Here it's 42. And if you see your R square is very high, and there is something called as your D statistic, which is called as Durbin-Watson statistic. I've yet not explained you what your Durbin-Watson statistic is. However, please make a note that this is a very critical test. Always remember 2-3 tests which are often asked in your in your master's examination, even in your entrances, or as MCQs in your net examination, is that they will also always ask you these critical tests. So always remember the white test for heteroscedasticity, which is one of the most widely used tests, apart from the other tests as well, and the Durbin-Watson test. There are two tests by Durbin-Watson. There is a D test and there is an H test. H test is not being explained in this particular chapter, but however you can find this in my class notes. We will go through what the Durbin-Watson statistic is, but just make a note that this is 0.14. Now, how do you detect it? As I told you, you have a graphical test, you have a Durbin-Watson D test, you also have a Durbin-Watson H test, which is a slight modification of that D test. I'll explain you what this test is. And you have a runs test. This runs test is actually not there in your syllabus. And then you have a Bush-Godfrey test, BG test, which is also called as Lagrange multiplier test. This is there in your syllabus, and often I've seen a question on this. Although you don't have a paper this year, but still this is a very useful test. You need to learn about that. Now, remember the graphical method that we had used in heteroscedasticity. I told you that is called as a Resi plot. Excuse me. Here, the graphical method in case of a time series data is called a time sequence plot. What you do is you plot the errors against time. Either you plot the errors against time, and in the case of this particular example, can you see there is a relationship here, and or what you can do is and this is a more, I like this particular format much more, because this particular format will definitely give you, in case of usual economic data, you will definitely get a positive autocorrelation. You will get this kind of a trend. So, or you can put it in this particular way. This is how you do it. Now I'll come to this particular table as well. But if you can see that you have ET minus 1, then you have taken a difference between the two, you have squared it, and you have done the ET square. Now I'll come back to this particular table as well, because this particular table explains you what we are going to do. As I told you, what you can do is you can just plot ET with the t minus 1, and you will find out the relationship between the two. And usually, as I told you, in case of economic data, you in 90% cases you have positive autocorrelation. Negative autocorrelation is just is not usually the case. Then, so the first case was your Durbin-Watson test. Then comes your second test and the most celebrated test, which is the Durbin-Watson D test. Now, what is the Durbin-Watson D test? Now, the D statistic is computed in this particular way. So, what you do is you check the errors, you subtract the error with the previous time period error, and square it. So, if there is a randomness, imagine there is a randomness in the errors. So one error will be positive, one error will be negative, one error will be positive, one error will, if there is a randomness in the errors, what will happen is these will cancel out with each other, and the ET and ET minus 1 will if there is no relationship between the two, this square term, and in fact the term, the relationship will be approximately equal to 0. So there is no relationship between them. However, if there is certain kind of relationship, either positive, so the errors are positively related to each other, or they are negatively related to each other, what will happen is that their square, the subtraction, or the absolute term if squared, or the positive relationship, in both the cases, because of the square term, this will be a positive number, and this will be, if there is a positive correlation or a negative correlation, this will be closer to 1. So what will happen in this case is that your D statistic will be something different from 0. So what it actually does is that it is simply a sum of square differences of successive residuals upon RSS, upon the residual square. So what essentially you do in this table is you have this square, you just squared these values, and if you see, please make a note that what has happened is this is time period 1. Remember, this is time period 1 and this is time period 2. This is time period 2. What happens is, in this particular D value, when you are subtracting the previous term, there is no previous term for this. So what happens in calculating the D is that you lose the first observation. Please remember, in case of Burgundy test, in case of D statistic, you lose the first observation because you have to subtract the error from the previous observation. So that's why there cannot be an error from the first observation itself, because there's no previous term. So that's why you lose one error term, and what you do is you just find out the sum of all of this, the sum of D square, and divide this with this summation of the RSS. This is essentially what you do. Now, coming to the valuation of it. Now what we have computed, so all of your statistical softwares always have this D statistic mentioned there, and suppose in our case we have mentioned this as 0.14. Now let's see that how do we go about calculating this, and how do we what are the assumptions in calculating the D statistic. These are extremely important assumptions. Please make a note of these assumptions, because you cannot run the D test without these assumptions. If these assumptions are violated, that means that you would have to use some other test rather than D test. Every year there is a question in your in your finals, or when you take your entrances, there will definitely be a question, and usually it's a trick question. That trick question usually is that there will be a violation of one of these assumptions, and you would be asked to apply D test, which cannot happen. You would have to apply either an H test, or the Bruce-Godfrey, or the Lagrange multiplier test. So please make a note of these assumptions. Now, what is the first assumption? That the first assumption is that the D test or the D statistic can only be calculated in a regression model which has an intercept term. If the regression model is a regression through origin, you cannot run the D test. So that is your first assumption. Your second assumption is that your X variables have to be non-stochastic, which is a very familiar assumption from the CLR. Then the third assumption is also very important, which says that the relationship between the error term can only be with the previous period error term. So there is a relationship between UT, or in our case, when you will have sample, the ET and ET minus 1. This relationship cannot be with UT minus 2. This row is basically telling you the quantum of this relationship, that what is the relationship between ut and ut minus 1. So essentially this is coefficient of autocorrelation. Remember the coefficient of correlation between two terms. However, this is the relationship between error terms, and this is not an exact relationship. See, this is not an exact relationship. You have an error term along with this. So you are saying that there exists a relationship between the error term and the previous term error term. But that can only be the previous term, cannot link to any more than any further down the road error term. This is called as Markov first order autoregressive scheme, or in short, this is called as AR1. This is called as AR1 modeling. So AR1 scheme is the first order autoregressive scheme. In the first order autoregressive scheme, your regression analysis, your errors are regressed only on the previous period error term and not any further. So the maximum lag is 1 period. That is why it is called AR1. Now your question can be, why can't we have second order autocorrelation? Yes, you can have, but the treatment is a little different. The test is a little different. The test is the H test. So what you have, suppose you have this kind of a model where your error term in this period is actually dependent on the previous term as well as the last to last term, which you will always find out in lag models. So imagine something like this. If the RBI changes the repo rate in this particular period, it is going to impact the money supply not only in the next period but in the subsequent 3-4 periods because of the inertia built into the system. So that basically how many periods it's impacting, that is called as the different AR. So if there are two different lags that you are taking, that is called as AR2. If you are extending this till period Q, that is called, the generalized version is called ARQ. So this is an important thing that you need to understand, what AR1, AR2 till ARQ is. However, we will be dealing with AR1 in this particular course. Then the fourth major assumption, again something which students ignore, is, and which is always a trick question, that your D statistic cannot be found if your regression has a lag term of the dependent variable. So suppose you are regressing GDP on say investment. Of course, you would also like to see that, because if previous term's GDP is low, that will have an impact on the next term's GDP. So something like, because of COVID, what is happening is this quarter's GDP is going down, and because of the inertia built in this quarter, the next quarter GDP is also going to be pretty low. So if you want to find out the GDP in the next quarter, you will definitely have to take the inertia or one of the dependent variables as the previous period's GDP. That is called as an auto-regressive model, where the dependent variable is also one of the lagged version of the explanatory variable of the dependent variable is an explanatory variable as well. So this is not allowed. This is not allowed in D statistic. However, if you use the Lagrange multiplier test, that is perfectly okay. So please remember, the D test that you do, the D statistic that you find out, is based on 3 solid assumptions. The first assumption being that you have you cannot have a regression through origin. The second is you can only have AR1, and the third is that you cannot have autoregressive modes. Given this, we can approximate that D can be approximated as this particular value, where rho is this. So if you want to learn more about it, let's go through our class notes and see how we come to find this. See this? In this particular case, I've mentioned the four particular assumptions that are there, and I am going to prove that how this is going to be the case. So if you have a large enough sample, then your d you can simply put this as the d value, and you will have the result. How will you have the derivation? Remember, this is on the basis of large sample. Now this was the definition of d that we had taken, that it is the difference between the one period error term upon the RSS. I just want you to open this term up and you will get a plus b whole square. And because of the fact that you have extremely large sample, the sum of squares of the sum of squares of the error in t period and the sum of square of t minus 1, that has only a difference of one particular period in this. What you are doing is you are summing up the error terms in period t, you are summing up the error terms in period t minus 1. So the difference between the two is just a one period. So in a very large sample, these will be very similar. So you can put this as you can take them as common. And when you take your two outside and you do a arithmetic manipulation, you will get this particular value, where rho is nothing but the estimated coefficient of correlation between ET and ET minus 1. So your rho is nothing but the coefficient of autocorrelation, but the estimated value. So the coefficient of autocorrelation can either be 0, which means there is no autocorrelation, can either be minus 1, which is negative autocorrelation, which is negative coefficient of correlation, and can be positive 1. And see, try to put in values. If you put the value of 0 here, where you are saying that there is no autocorrelation, the value of d is coming out to be 2. So when your d statistic is close to 2, you can assume that there is no autocorrelation in the data. If you put this value as minus 1, so minus 1 minus 1, you will get d statistic value as 4, which will show you that you have perfect negative autocorrelation. So if your d value is close to 4, you have negative autocorrelation. And if you put this value as 1, so 1 minus 1 will be equal to 0. So if your d statistic is equal to 0, then you have perfect autocorrelation. So in fact, what you will find out is, in general economic data, your d statistic will be actually very close to 0. As I told you that you usually find the case of positive autocorrelation in time series data. So although your this is the range of your d statistic. I hope with this particular analysis you're able to understand what is the range of your d statistic. Now coming back to our analysis. So we now know how we got this particular rho value. And through this rho value, now we know that if rho is equal to minus 1, which essentially means there is negative autocorrelation, the approximate value is 4. If there is no autocorrelation, the value is 2, and there is perfect autocorrelation, the value is 0. So the range of computed d is between 0 to 4. Now, you have, similar to all of your earlier statistics like t statistic, chi-square test statistic, f statistic, that means you will have to have a critical value that you need to compare this computed d. You have a computed d, which you have from your statistical software. Remember, we have 0.14 in our example. Now you need to compare this with certain critical value. This is how you do hypothesis testing. Critical d. So instead of a critical d, you actually have two critical d's, dl and du, d lower value and d upper value. Why do you have two d values? Because remember, there is a huge range. There is a range from 0 to 4. In between, you have if it's close to 2, you have no autocorrelation. If it is closer to 0, you have positive autocorrelation. If it's closer to 4, you have negative autocorrelation. There is presence of autocorrelation, but in between there is no value. So that means that essentially can give you a hint that you will have 2 critical D values rather than 1 critical D value. Now, how do you calculate this? If you want to see this, I can show you this well. In all of your data, you have D statistic values. Can you see this particular table? This is your Durbin-Watson D statistic table. Now this D statistic will give you a DL and a DU at 5%. Similarly, you have a table for 1% as well. Now you will have certain parameters. These parameters are given, the number of parameters are given here from K is equal to 1 till K is equal to 20. You have these parameters given. See, we'll see what these parameters are, and you have the number of observations in your data. So this data will have this entire table will be calculated from 6 observations till 200 observations. So this is the range. We will see how we calculate this. Now let's see this. What's the procedure? The procedure is very simple. What you do is you calculate the OLS regression and estimate the residuals ET. Now from the residuals, what you can do is you can compute D. It's very easy. What you need to do is summation ET minus 1 upon, you have summation ET square. See this particular value. So, and remember this is being from T2 till T9. This is from 2. Why the second observation? Because the first observation has no previous term till N, and this is from 1 to N. You will find out the value of rho, and from the value of rho you can find out the value of D. This is how you will find the value of your D statistic. Now what you need to do is you have the number of observations with you. Suppose in our case the number of observations are 50. Our sample size is 48, so the most closest one is 50, and you have to check at 5% level of significance. So you need to find these 2 different values, and how many this thing K is there? You only have 1 K. You have only one explanatory variable. Remember, this is excluding the intercept term. So what you do is go to the D table, the Durbin-Watson D statistic. See the observation, number of observations 50. You have K is equal to 1, and you have 2 different values. So you have a value of 1.5 and 1.58. These are the 2 critical values, GL and DU. Now you go back and you will find that these are the exact same values at 5%. So you have a DL which is 1.5, and you have a DU which is 1.58. This is 1.50, 1.5. And this, remember, this is 4 minus GU. So this is the range where you will say there is no autocorrelation, either positive or negative. There is no autocorrelation whatsoever in this particular range. However, in this range, see this particular range, if your calculated D value is less than DL, the lower limit, that definitely tells you that your data definitely suffers from positive autocorrelation. You have evidence of positive autocorrelation. And if your data has extremely high D value, suppose your D value is 3.6, so 4 minus 1.5, this is essentially what you are doing. 4 minus 1.5, this value will be coming out to be 2.5. So if your calculated D statistic the statistic is 3.6, that essentially means you are coming in this your estimated or your calculated d statistic is here. That shows your data has definitely got negative autocorrelation. But if your d statistic is in this range or is in this range, 1.2 this or 2.2, if it's in this range, 2.5, is it 2.42? Yeah, 2.4. Or if it's in this range, so you cannot make a decision here. You cannot make a decision here. You cannot make a decision here. This is the zone of indecision. You cannot say whether you have positive. You have a positive autocorrelation in this zone. You cannot say you have a negative autocorrelation. You can definitely say you definitely do not have a positive autocorrelation here. Similarly, you can definitely say that you do not have a negative autocorrelation, but you cannot also say certainly that you don't have autocorrelation. If your d value is coming in between this zone, you can definitely say there is no autocorrelation. So this is how you check this. Remember, in our example, our d value was 0.14, which is way here, which essentially translates into the fact that we definitely have positive autocorrelation. See, this is the rejection. This is the decision rule. Please have a look at this decision rule. I have explained you this particular decision rule using that particular diagram. Coming to other tests, so we also have a Durbin-Watson H test, and you have a Bush-Corporate test. We will see these two tests as well. Let's actually have a look at these two tests. In case of a Durbin-Watson H test, what your H statistic? Remember, in case of your B test, you had a D statistic. Here you have a H statistic. And what is your H statistic? It is 1 minus, this is actually equal to rho hat, and you are dividing, you are multiplying this by n upon 1 minus n into the variance of the parameter where your lagged variable is there. So your H test, remember, if you remember, one of the assumptions of the D test was that the D test cannot be used when you have a autoregressive model. That means when one of the explanatory variables is coming out to be a lagged version of the dependent variable. This, remember, this was not allowed. Suppose this is the regression that you have. So this is the parameter B3. So the variance of B3 is coming out to be here, and this H, so you calculate this H statistic, which is often given by all of your computers softwares, and this H test has a normal distribution and a standard normal distribution, in fact. And your if you reject your null hypothesis is that there is no autocorrelation, and your alternative hypothesis there is presence of autocorrelation. So this is a simple test, but this test is used when you have autoregressive models. Now coming to the Bush-Corporate test, which is also called as the Lagrange multiplier test. Now the Lagrange multiplier test is used when you have a ARQ scheme. Remember, in the case of D statistic, you can only have AR1. Only the previous period lag term can be there. However, here what we have is you have the previous Q periods lag term. Now, how do we decide what Q will be? There is something called AIC test. You don't need to get into what AIC is, but there is something called an AIC test which tells you till what Q period you will take this. So your error term in this particular period is actually dependent on not only on the previous period, not only on the previous to previous period, but till the previous Q period as well. And you are estimating this regression. So this is the normal regression equation that we have. And what we now do is run a auxiliary regression. This is something similar to, if you remember, this is something similar to white test as well. You used to have a general white test where you were running the regression of the error square on not only on all x variables but different cross products, different squares, cubes, different functional forms. Similar to the spirit is very similar. Instead of the square term, you have the error term being regressed on the normal explanatory variables, but also on the functional form, different functional forms of the ARQ. So you will regress this on ARQ as well. Now, and you can also take the lagged, you can also take independent variable as y minus t. So that is also allowed in case of Gauss-Godfrey test. Now, what you do is you calculate the R square of this particular auxiliary regression, and as in case of white test, n into R square is going to approach a chi-square distribution with q degrees of freedom, where q is the ARQ, how many previous terms are included. In case of the white test, if you remember, you had this degrees of freedom as the number of terms minus the intercept. And if this is coming out to be significant, if this probability is coming out to be significant, you will say that you have the presence of autocorrelation. If it's not, then you say you don't have autocorrelation. And this is the other way. Have a look at this. The F test to calculate the same. This is another way to test the Gauss-Godfrey test. So I've explained you. I've explained you the two tests. Now let's go forward towards the last part of our discussion is the remedial measures. Now the remedial measures are extremely simple. Now what you do is either you know the relation, what is the relationship between the terms. So if you know rho, if you know, and if rho is known, that means you can estimate this particular regression. And if that is known, what you can do is you can simply modify your regression. This is the previous period regression line. This is current period regression line. What you do is just subtract both of them. So what you do is multiply this entire with rho. This is what you will get, and then subtract your this period with the rho into this particular line. So this is your 2 and this is your 1. So if you do 1 minus 2, you will get this particular regression line. Now remember, your new error is ut minus rho ut minus 1. Ut minus rho ut minus 1 is Vt, and your Vt, the error term, now has the OLS assumptions. So this is not, your Vt is not autocorrelated. Vt and Vt minus 1 is not autocorrelated. So that essentially, and you can write this as B1 star, you can write this as B2 star and B2, and this is as X star, and your B1 and then your this is how you will put this up, and this regression is now the transformed variables, and the estimators that you have B1 star and B2 will have the desirable property of blue, and this is what is called as generalized least squares. And these are also called as generalized difference equation, because what you're doing is you're running differences between two different regressions. You're actually running a difference form of a regression. And in this entire process, what you are doing is, because you are running yt minus 1, essentially what will happen is, if you run this as y, you will lose out y1 and x1. Why? Because there will be no corresponding value to subtract it from. So essentially your data will start from x2, y2. So that is why you will lose out these y1 and x1. And if you have a very small sample with you, then losing out a particular observation is a huge loss. So what you have is, there is a transformation like this, x1 star and y1 star, which actually replaces the first observation. So you can use the Price-Winston transformation to regain the first observation that you have lost. Then the last part, suppose you do not know the row, then what you can do is you can have the first difference. So you can assume row equal to 1. As I told you, in most econometric data, your row is equal to 1. You have positive autocorrelation. So what you do is you just subtract these two and you will get this particular regression line. Remember, you subtracted, you don't have any intercept term. Therefore, this is a regression through origin. And lastly, if you still don't have any, you don't want to take this particular value, what you can do is you can estimate the row from the statistic. The way that we have, the way this was given as 1.4, and from that we can estimate the row hat, and then on the basis of this row hat, what you can do is you can subtract. You can estimate this particular regression. You can estimate this particular regression, and on the basis of this, you have this particular regression being estimated. So this is how you can actually estimate your row, and you can convert. Again, what you are doing is you are transforming your data into a non-autocorrelated data by subtracting it with the previous terms, previous periods data. So this is what is called as the method of GLS, and this is how you actually get rid of the problem of autocorrelation. So this was our entire discussion. This was our entire discussion on autocorrelation. This part of the chapter is not in your course, so you don't need to cover this up. And I hope you go through the questions of this particular chapter, because this is an extremely important chapter for your, even at your master's level. If you have doubts, you can always come back. So I thank you for attending this session. Bye bye.